Okay, can I have everyone's attention, please? So let's go ahead and start. Quick announcement, and that is that I noticed that during the last 2 days, there have been a lot of people adding this class, all right? If you were one of those late people who added this class, just keep in mind that there are online homework that has to be completed. And if you're transferring from another class, your scores are not transferable, so please contact me if you've switched classes. The second is, if you join this class late, I want to remind you that there is a survey that you have to complete by the end of this week, all right? And so you will get credit for that, completing those surveys, and so please make sure that if you transferred into this class, that you complete that survey as well. Okay, so getting back to where we stopped last time, if you guys remember, we talked about bases last time, and if we wanted to just summarize the important features of bases, we said that firstly, so we're going to draw the same parallels between acids, okay? So strong bases have Ka greater than 1. We know that weak bases have, sorry, we're talking about bases, so it should be Kb. Weak bases have Kb less than 1, okay? 2, the smaller the value of Kb, the weaker the base. The third point that I want you to remember is substances that have Kb less than 1 times 10 to the negative 14 do not act as a base in water. All right? Because we know now water has a higher Kb and will act as the base. All right? Now lastly, we finished up by saying that we derived an expression where we said Ka times Kb equals Kw, which is 1 times 10 to the negative 14. Where Ka gives you the acid dissociation constant for the acid form of the conjugate acid-base pair. And Kb gives you the base dissociation constant of the conjugate base of that acid, all right? And so we said that very often only Kas are listed in tables. And so if you're looking at the conjugate base and you want the Kb value that corresponds to that conjugate base, all you have to do is convert Ka to Kb, all right? And then we said that since these scales are enormous, we also look at it in terms of the logarithmic scale, and so we said if you take the negative log of Ka and the negative log of Kb, that will give you the negative log of Kw, and so that gives you pKa plus pKb equals pKw, all right, which, as all of you know, is equal to 14. So if you refer back to your notes from last class, in my haste, I wrote pKw as 1 times 10 to the negative 14. So can you cross that out and make sure that you don't make that mistake, all right? And that it is actually 14, all right? So this is worth remembering, because now if you remember this basic fundamental information, now it makes it easier to solve problems. So we're going to take some examples. And if you remember, I gave you a task, and I hope many of you completed it, because I'm going to quickly go through the answer now. So if you guys remember, we looked at a problem last time where we were looking at calculating the pH of a weak acid. And we were told to begin with, we had 1 mole of the acid dissolved in 1 liter of water. So we know that concentration is moles per liter, and therefore, to begin with, we know the initial concentration of acetic acid. And so the initial concentration of acetic acid is given here. It's given to 3 significant figures, so we'll place that there. And then, of course, to begin with, we have no reaction taking place. This is at the point at which the reaction starts, so it's at time 0, all right? So because we have 0 hydronium ion and 0 acetate ion, all of you recognize that the reaction has to proceed in the forward direction, all right? And if the reaction is proceeding in the forward direction, we know that the amount consumed or the amount reacted would be negative x. The amount formed would be plus x, all right? And therefore, at equilibrium, we'd have 1 minus x, x, x. So we're kind of keeping track of the concentrations of all the species that are there in solution. And we know that we're looking at the acid dissociation constant, and therefore, that is 1.76 times 10 to the negative 5. So we know Ka is 1.76 times 10 to the negative 5. That equals the concentration of the hydronium ion times the concentration of the acetate anion divided by the concentration of acetic acid, which gives you x squared over 1 minus x. Now, remember, look at the K value. This is 10 to the negative 5. So this is an enormously small number. And so we know that if it is a small number, if the reaction is proceeding in the forward direction, the extent of that reaction is going to be really small. It's going to, all right? And therefore, we know that x is going to be small. And so it is safe to make the approximation. And so we make the approximation, and you can see that once I make the approximation, things get to be really simple. So I know 1.76 times 10 to the negative 5 would be x squared over 1. And therefore, if you solve for x, it comes out to be 4.20 times 10 to the negative 3 molar. All right? And so once you know that, what do I need to do next? You have to validate. Remember, if you make an approximation, you have to check whether your approximation is validated. Okay? So validate approximation. And when you validate the approximation, remember our approximation is that x is really small compared to 1, which is 4.2 times 10 to the negative 3 molar divided by 1 molar times 100, which gives me 0.42%. So that falls well below our threshold, all right? And what this means is that, that we can make this approximation, all right? And so now that I know this is valid, I know that the hydronium ion concentration equals x, which equals 4.20 times 10 to the negative 3 molar. And if I know the hydronium ion concentration, I can take the negative log of that, and that comes out to be 2.377. All right? Again, this is a 3 significant figure number. Therefore, when you record it in pH, you're going to go to 3 decimals. All right? Now, that was the first part. The second part is calculate the percent dissociation. All right? So the percent dissociation, or percent decomposition, or percent ionization would be the amount that dissociated, which is x, once again, divided by 1 molar times 100. And therefore, this would be 4.20 times 10 to the negative 3 molar divided by 1 molar times 100. And we just did this calculation to check validity as well, and that was 0.42%. So what does that mean? It means that for every 1,000 molecules of acetic acid that you put in, 4 will dissociate. Does that make sense to everybody? So the percent dissociation gives you the percentage of molecules, acetic acid molecules that dissociated. So for every 1,000 molecules that you put in water of acetic acid, only 4 will dissociate. So that is a really weak acid. Can everybody see that? Because opposed to that, if you had a strong acid, what would a strong acid do? If I put 1,000 molecules of acid in the water, what would a strong acid do? All 1,000 would dissociate. All right? So there's a dramatic distinction between strong acids and weak acids. Okay? Now sometimes, you guys are all carrying out online homework, and you're seeing some of these problems come up in the online homework. And sometimes the reverse is given to you. All right? Sometimes they give you the percent dissociation, and you're asked to calculate Ka. Or sometimes you're given the pH of the solution and asked to calculate the initial concentration. So if you're given the pH of the solution, what would your strategy be? If you're given pH, what do you want to convert that to? The hydronium ion concentration, the molarity of the hydronium ion concentration. All right? Now, once you know the hydronium ion concentration, if you know what Ka is, now hydronium ion concentration is the concentration at equilibrium. All right? So that means that all you have to do is you're just working backwards. So you'll see the problem where now, if you're solving a problem of that type, all you have to do is now you don't have to look at initial change in equilibrium. All you have to do is look at this. And you would say, this is the hydronium ion concentration. If this is hydronium ion concentration, this has to be the same as that. Do you guys see that? And this is what you need to find out. What is my concentration at equilibrium? All right? And my concentration at equilibrium will be approximated to be similar to the initial concentration. Does that make sense to everybody? Because for all weak acids, this x is so small that you can approximate it. All right? And so what you're doing is you're just working backwards. You know what the equilibrium concentration of hydronium ion is. If you know the equilibrium concentration of the hydronium ion, you can calculate the initial concentration of the acid. Okay? So you're seeing these kinds of problems coming up in homework, and now you should be able to solve the problems, and where you can get many different variations of this, and you should be able to solve it. Okay? Now let's take one last example before we move on to the next topic, and let's take an example of a base. So here we have calculate. So now we're looking at calculating the pH of a conjugate base, all right, or a base in water. So calculate the pH of a solution made by dissolving 0.01 moles of ammonia in enough water to give 1 liter. All right, Kb is given. So once again, the starting point is for you to recognize that you're starting with NH3. And we know that NH3 acts as a base in water. All right? And if you're not sure, go to the table and look at the values. All right? So if you take ammonia, you can see that ammonia should be somewhere in here. Keep going down. Oh, there we are. All right. My eyesight is really bad. So here's ammonia. This is the basic form. This would be its acidic form. The ammonia down here is way below this. And we know that ammonia can't act as an acid in water. Can everybody see that? So because water is a stronger base, ammonia has, all right? So this can't act as an acid in water. So if I take ammonia, then the equilibrium that would be established would be NH3 plus liquid water, giving me, what would I get? NH4 plus, which is the conjugate acid, and OH minus. All right? And Kb is 1.8 times 10 to the negative 5. Okay, so you have to identify what the equilibrium is, and you have to identify whether it's going to act as an acid in water or whether it's going to act as a base. Because this acts as a base in water, the equilibrium expression would be Kb. All right? So we've written the information down. Now we need to start with the initial concentration. So the initial concentration of ammonia is 0.1 moles in 1 liter. Okay, so that means you have 0.01 molar solution to begin with. We're not concerned about the concentration of water. And before any any reaction takes place, we're going to have 0 products being formed. So once again, we know that to establish equilibrium, the reaction has to proceed in the forward direction. Therefore, a change would be negative x plus x plus x. At equilibrium, the concentrations would be 0.010 minus x, x, x. All right? So we follow the same process that we did when we calculated the pH of a weak acid. All right? But here, we are now looking at Kb. So Kb equals 1.8 times 10 to the negative 5, which gives us the concentration of the conjugate acid NH4 plus times hydroxide ion divided by the concentration of NH3, which gives me x squared over 0.010 minus x. All right? Now, if you wanted to, you can solve the quadratic equation. It's going to take you longer, but as all of you know, if you look at the K value, Kb is 10 to the negative 5. So you might as well take the approximation and then check the validity. All right? So if we make the approximation, we know that 0.010 minus x will approximate to 0.010. And therefore, we can say 1.8 times 10 to the negative 5 gives me x squared over 0.010. And therefore, if you solve for x, we are going to 2 significant figures. So it comes out to 4.5 times 10 to the negative, 4.2 times 10 to the negative 4 molar. Okay? So what that means is that we calculated x. And so in this equation, can everybody see that what we're calculating is hydroxide ion concentration? So hydroxide ion concentration equals x equals 4.2 times 10 to the negative 4 molar. But is that what they ask us to calculate? What do we need to figure out? pH. So that means if I want pH, I need to now convert the hydronium ion concentration and figure out how much, the hydroxide ion concentration and convert it to hydronium ion and figure out how much hydronium ion is there in solution. All right? And so there are 2 ways you can solve for this. One way is to say we know that the hydronium ion concentration equals Kw divided by hydroxide. And therefore, that will be 1 times 10 to the negative 14 divided by 4.2 times 10 to the negative 4. And that number comes out to be 2.4 times 10 to the negative 11 molar. And now that I know the hydronium ion concentration, I can figure out pH, which comes out to be 10.62. So now I take the negative log of that number, and that gives me the pH. Because we're carrying 2 significant figures, the answer goes to 2 decimals. All right? Now, another way to do this is to take the hydroxide, calculate pOH, take the negative log of that pOH, and then subtract that from 14, and you should end up with the same answer within round off. All right? Okay, any questions up to this point? So now you really need to spend some time practicing problems involving acids and bases, all right? And the homework that we've assigned and also the problems that you're working in discussion will kind of reinforce that, all right? Now we're ready to move on to the next topic. And the next topic that we're going to look at are polyprotic acids. So if you remember, up to this point, we have looked at monoprotic acids. All right? Up to this point, the examples that we've looked at are monoprotic acids. These are acids that have only one dissociable proton. All right? So monoprotic acids are acids that have only one dissociable proton. So examples that we looked at were things like, we looked at HCl. This has one dissociable proton. It's a strong acid. It has one dissociable proton. We looked at acetic acid. And we said even though if you look at the structure of acetic acid and the structure has 4 hydrogen atoms, only one among those is actually acidic and is dissociable. So once again, acetic acid is a monoprotic acid. If you take something like hydrogen cyanide, that's a monoprotic acid. If you take HF, that's a monoprotic acid. All right? And if you take something like formic acid, that is also monoprotic. So if you look at the structure of formic acid, it has 2 hydrogen atoms in that molecule. But remember, every hydrogen atom in a molecule does not have to be acidic. All right? And so these are all examples of molecules that are monoprotic. All right? Polyprotic acids have more than one dissociable proton. And examples include examples like H2SO4. All right? Now remember, these are all in aqueous solution, so we can say that they're aqueous solutions. And so we're in aqueous solution. And you can see that now this has 2 dissociable protons. Both of these protons can come off. All right? Another example would be H2CO3. All right? H2SO3. These are all examples of polyprotic acids. And if you look at this, all of these have 2 dissociable protons. They're called diprotic acids. So diprotic acids have 2 dissociable protons. All right? Now, other examples include, like you can have H3PO4. Now, this has 3 dissociable protons. And another would be like H3ASO4 aqueous. So these are called triprotic acids. And triprotic acids have 3 dissociable protons. So all of these are collectively called polyprotic acids. All right? So now we're going to look at acids that have more than one dissociable protons. All right? And let's take some examples. We'll start by looking at something like sulfuric acid. So it turns out if you take polyprotic acids dissociate in a stepwise manner. All right, so when you look at the dissociation of protons from a polyprotic acid, each proton comes out sequentially in a stepwise manner. All right? So if I take an example like sulfuric acid, let's start with sulfuric acid. So all of you recognize that sulfuric acid is H2SO4 and that it has 2 protons that can be dissociated. All right? So what happens is that first, one proton comes off. So if you take H2SO4, and this is in water, remember, this is the acid, and this would be the base. All right? And so the protons come up stepwise, all right, in sequence. All right? So the first proton will come off, and when the first proton, the acid donates that proton to the water, which is the base, what you end up with is H3O plus. Now, if you take H2SO4 and pull a proton off, what do you end up with? HSO4, remember charge balance, so it's going to be HSO4 minus, okay? Because you took an H plus off, that means this has to be HSO4 minus. A quick way to check is on the reactant side, you can see that everything is electrically neutral. All right? Therefore, on the product side, we know that the hydronium ion has a positive charge. Therefore, this has to have a negative charge. All right? And this is the conjugate acid, and this would be the conjugate base. Now, since this represents acid dissociation, we call this Ka1, because now this refers to the first proton coming off. So for polyprotic acids, we will call this the first acid dissociation constant, or the first acid ionization constant, all right? Because this refers to the first proton coming out. Now, in the case of sulfuric acid, this number is of the order of 10 to the 2. All right? And so it's of the order of 10 to the 2. So the first proton coming off, does that act as a strong acid or is it acting as a weak acid? Strong. And because it's acting as a strong acid, we know that the first proton coming off will be a complete dissociation. So all of the H2SO4 will convert to H3O plus and HSO4 minus because now it's acting as a strong acid. All right? Now, the second step will involve the second proton coming off. So now we take this, all right, the species that is formed when one proton has been taken off. Now, sequentially, the second proton will come off. And you end up with, what do you think the product is going to be? Now, if you take HSO4 minus and now pull the proton off, what are we left with? SO4 what? 2 minus, all right? So once again, we are maintaining charge balance. And check, on the reactant side, we start with -1. Therefore, on the product side, you have to have -1 as well. So you have a plus here. This has to be 2 minus, so the end result is that you have charge balance. Now, since this involves removing the second proton, we call that Ka2. And Ka2 turns out to be, and you know, you can find these values in this table, and I will come back to that, but it turns out it is 1.2 times 10 to the negative 2. All right? And so for the second step, now this is the acid. This would be the base. And then for the reverse reaction, this would be the conjugate acid, and this would be the conjugate base. All right? And when this equilibrium is established, the equilibrium constant that corresponds to the second equilibrium is Ka2, and we call that the second acid dissociation constant. All right, now let's take a look at the HSO4 minus that is formed. Can you see that in the first equilibrium, HSO4 minus is acting as a base? It's a conjugate base. All right, so something that acts as a base in the first equilibrium now acts as what in the second equilibrium? As an acid. So you can see that HSO4 minus is actually acting as an acid as well as a base. All right? And what do we call substances that act as an acid as well as a base? Amphoteric. So you can see that in this HSO4 minus is amphoteric. All right? So the way we consider this is in a stepwise process, and we say that these are two competing equilibria that are taking place at the same time. All right, so you're having two competing equilibria occurring at the same time. The first involves the deprotonation of the first proton, and then the second step involves the deprotonation of the second proton. All right? So now I want you to kind of, before we start doing any calculations, you should be able to look at this entire picture and kind of figure out what are the major species. So once equilibrium is established and you have both of these competing equilibria taking place, what do you think will be the major species? All right? So let's look at the first step. The first step, when equilibrium is established, is it towards products or is it towards reactants? Products. You're going to have lots of H3O plus and H2SO4 minus. Because it's a strong acid, for all intents and purposes, we can say that there's 0 H2SO4. That number is so small that we're going to ignore it. All right? So for the first step, what is the major species? H3O plus and H2SO4 minus. All right? Now let's go to the second step. The second step, it's acting as a weak acid. Now when you have a weak acid, does that lie on the reactant side or does it lie on the product side? Reactant side. So for the second equilibrium, much of it is going to be H2SO4 minus. Do you see that? And very little actually is going to go to SO4 minus and H3O plus. Does that make sense? So what we can say is in this equilibrium mixture, we can say at equilibrium, major species. So if you want to have a feel for what that equilibrium composition looks like, the major species are going to be H3O plus and H2SO4 minus. And the minor species will be SO4 2 minus. Did you guys get that? All right? And we're not going to consider H2SO4 to be a minus species because it's a strong acid and H2SO4 will dissociate completely. And so the amount of H2SO4 that's left over is going to be so minuscule, hardly anything at all. All right? And so this is what the equilibrium composition would look like. All right? The hydronium ion concentration comes from two sources. There's going to be a large amount of hydronium ion coming from this step, and then there's going to be a tiny amount of hydronium ion coming from this. So between this amount is, you're going to add the amount of hydronium ion from this to this. Do you see that? But the amount that comes from this is so small that, you know, adding these two together will amount to adding that. Do you see that? Just that component. All right? Now let's take another example of a diprotic acid, and in this case, let's take carbonic acid. So if I take carbonic acid, which is H2SO4 aqueous, once again, it's a diprotic acid, and if it's a diprotic acid, I can write the two competing equilibria. All right? So the first step would be H2SO4 aqueous plus water, giving me H3O plus aqueous plus HCO3 minus. This is the acid, this is the base, conjugate acid, conjugate base. And now, the first dissociation constant for carbonic acid is 4.3 times 10 to the negative 7. All right? The next step will be the second proton coming off. So now, what is a base will act as an acid, and this will now protonate a water to give you hydronium ion plus CO3 2 minus aqueous. And this is Ka2. And Ka2 comes out to be 4.8 times 10 to the negative 11. All right, so if I take carbonic acid, which is H2SO4, the first step, it acts as a strong acid or a weak acid? Weak acid. Look at the K, it's 10 to the negative 7. So it's acting as a weak acid. And then the second step is acting as even a weaker base. So if I want to look at the equilibrium composition now, the first step is a weak acid. So where does the equilibrium lie? Does it lie towards reactants or does it lie towards products? Reactants. So to begin with, you're going to have lots of reactants. All right? So in the first step, you're going to have the major species in the first step would be what? H2CO3. So in this equilibrium, the major species, so at equilibrium, major species would be H2CO3. You're going to have lots of that. All right? Now the minor species would be HCO3 minus and H3O plus. You see that? Because for the first step, the equilibrium lies on the reactant side, so they're forming only a very small amount of products. Now the products that are formed in the first step are the ones that dissociate to give you the second step. So if you're starting with small amounts to begin with, so you have really small amounts of this, and this is what goes in here. Can everybody see that? Now, if you look at the second equilibrium, where does the second equilibrium lie? Towards reactants or towards products? Reactants again. This is even less. This is 10 to the negative 11. So that means this equilibrium lies on this side as well. All right? And lastly, really, really small amounts, minuscule amounts. You're going to end up with minuscule amounts of CO3 2 minus. So if you're going to compare the relative concentrations, you know that H2CO3 will have the greatest concentrations. Then comes H3O minus and H3O plus, and then that should be greater than CO3 2 minus. So if you look at the relative concentrations of all the species in solution at equilibrium, now you have an idea what that composition is going to look like. All right? And it would look like that. All right? Now lastly, I want you to notice that always Ka1 will be greater, sorry, the other way around. Ka1 will be much greater than Ka2 and will be greater than any subsequent protons that come out. All right? So always, the first equilibrium constant will always be bigger than the second one. Because it turns out it's easiest to pull the first proton off. Now, pulling the second one off gets harder. And the reason is when you pull the first one off, you end up with a species that is negatively charged. So when you have something that's negatively charged, it's harder to pull something positive away from it. So when the proton forms, it's hard to pull that away. All right? And so sequentially, it becomes harder to remove the proton. And therefore, the Ka values sequentially get to be smaller and smaller. Okay? Now, if you take a triprotic acid, phosphoric acid is an example of a triprotic acid. And so if you take a triprotic acid, we start with H3PO4 aqueous plus water will give me H2PO4 minus. I took one proton off of this, and therefore it will be minus one charge, plus H3O plus aqueous. That will be Ka1. Now H2PO4 minus aqueous will now act as a base, an acid, to donate a proton to water, so that you end up with HPO4 2 minus and hydronium ion, aqueous. So this is Ka1, this would be Ka2. And then if you take HPO4 2 minus, acting as the acid, all right, you'd end up with PO4 3 minus, aqueous, plus H3O plus aqueous, and that would be Ka3. So you can see that Ka1 would be greater than Ka2, will be greater than Ka3. All right? So as an exercise at home, I would like you to see whether you can kind of figure out what is the major species in this solution and what are the minor species in that solution. All right? So if you turn to the table that I've given you, The Ka values for these can be found in that table. All right? And so if you look at this, all right, if you look at sulfuric acid, you can see that within parentheses you'll see a 1. That means when you see 1, it means that's when the first proton comes off. So this is Ka1, and if you go down this list and look for sulfuric acid within parentheses 2, that will be the second ionization constant. All right? Now if you take oxalic acid has 2 protons that come off. Here's the first one, here's the second one. If you take phosphoric acid, it's a triprotic acid, so there are going to be 3 protons coming off. The first one will have 1 within parentheses. Here is the second one, which is phosphoric acid with 2 within its parentheses. And then the last phosphoric acid is 3 within parentheses. All right? And so these K values correspond to the first, second, and third acid dissociation constants. All right? So now we can take a problem, and so now things get a little bit more complicated. So we can take a problem where now we can look at the concentrations of all the species in solution. So now we can calculate what are the concentrations of all the species in solution. So the question is, calculate the concentration at equilibrium of H2SO4, HCO3 minus, CO3 2 minus, and H3O plus in a saturated aqueous solution of carbonic acid in which the original concentration is 0.034 molar. So if you're solving a problem that involves a polyprotic acid, the same rules apply, the same approach applies, but you're going to do it stepwise. You're going to start with the first equilibrium, and then you're going to proceed to the second one. Okay? So let's start with carbonic acid, and we know that the first, this is a polyprotic acid, and it's got 2 dissociable protons. So in water, we'll start by looking at the dissociation of the first one, giving you H3O plus aqueous plus HCO3 minus aqueous. And this represents Ka1, and the value for Ka1 is 4.3 times 10 to the negative 7. So this acts as a weak acid. We know that the initial concentration is given. So the initial concentration of this is 0.034 molar. This is the amount before any reaction takes place. So we know that this reaction proceeds in the forward direction. Therefore, the change would be where the reactant is consumed and products are formed. All right? So at equilibrium, we have 0.034 minus x. This will be x and x. All right? So we can say Ka equals 4.3 times 10 to the negative 7 equals the concentration of hydronium ion times the concentration of H3O minus divided by H2SO4, which gives me x squared over 0.034. Okay? Minus x, and we'll make the approximation. Okay? So we know that this number is 10 to the negative 7. So the extent of the reaction is going to be really small. We know x is going to be small, so we can approximate that. And our approximation is going to be that 0.034 minus x will approximate to 0.034. All right? So 4.3 times 10 to the negative 7 gives me x squared over 0.034. Therefore, I can solve for x. And if you put those values in your calculator, the number that you end up with is 1.2 times 10 to the negative 4 molar. Let me see I got the right number. All right? So if you put that in your calculator, that's what you would end up with. If you check validity, validity would be 1.2 times 10 to the negative 4 molar divided by 0.034 molar times 100, and that comes out to be 0.36%. So you know that that's well below your threshold for approximation. So we know that this approximation is valid. And so now I can say, since I know what X is, I can say that my H2CO3 concentration would be 0.034 minus X, which is 0.034 minus 1.2 times 10 to the negative 4, which actually is 0.034. The amount that dissociates is so small that it does not make a difference in this number within the appropriate number of sig figs. All right? So if I want to calculate the hydronium ion concentration, the hydronium ion concentration is 1.2 times 10 to the negative 4 molar. And my HCO3 minus concentration is 1.2 times 10 to the negative 2 molar. Okay? So this is the concentrations that are related to the first equilibrium. All right? Now we need to look at the second step. The second step is where now HCO3 minus aqueous gives me reacts with H2O to give me H3O plus aqueous plus CO3 2 minus aqueous. And this would be Ka2. And Ka2 is 4.8 times 10 to the negative 11. All right? So now, for the second step, my initial concentration would be the concentrations that come from the first step. Can everybody see that? Because they're moving in a stepwise manner. So what would my concentration of HCO3 correspond to? It should correspond to the number here. All right? So to begin with, I have 1.2 times 10 to the negative 4. I'm not concerned about the concentration of water. Over here, what would my concentration of hydronium ion be? Is it going to be 0? No, we already have hydronium ion that comes from the first step. Can everybody see that? And the hydronium ion that comes from the first step would be this. So this would be 1.2 times 10 to the negative 4, and then that would be 0. So for the second step, these are my initial concentrations of all the species for the second step. So now I'm going to look at change. And just to distinguish between the X up there from the values here, I'm going to say this is going to be negative Y. All right? This will be plus Y, and this will be plus Y. All right? Therefore, at equilibrium, I would end up with 1.2 times 10 to the negative 4 minus Y over here. Hydronium ion concentration would be 1.2 times 10 to the negative 4 plus Y, and that would be Y. All right? So now I'm looking at the second step, and in the second step, I can say Ka2 equals 4.8 times 10 to the negative 11, which equals the hydronium ion concentration times CO3 2 minus divided by HCO3 minus, which gives me 1.2 times 10 to the negative 4 plus Y times Y divided by 1.2 times 10 to the negative 4 minus Y. Okay? Now remember, this Ka is 10 to the negative 11. All right? So I know that I can make this approximation because the Ka value is so small that we know this equilibrium lies entirely on the reactant side. So if I make the approximation that 1.2 times 10 to the negative 4 plus Y would approximate to 1.2 times 10 to the negative 4, and 1.2 times 10 to the negative 4 minus Y would approximate to 1.2 times 10 to the negative 4. All right? And once you make this approximation, I can say that 4.8 times 10 to the negative 11 equals 1.2 times 10 to the negative 4 times Y divided by 1.2 times 10 to the negative 4. And you can see both of those cancel out. So Y gives me 4.8 times 10 to the negative 11 molar. All right? And at this point, you should check validity. All right, I'm going to just skip that step, but can you guys check validity at home? You have to check whether y is really small compared to that. You can see this is 10 to the negative 11. This is 10 to the negative 4. So that number is really small. Okay? And so we can finish up by saying that the CO3 2- concentration would be 4.8 times 10 to the negative 11. All right? And in fact, you can see that this actually equals Ka2. Because these two concentrations will always cancel out, your carbonate concentration will come out to be that. All right? So now you can list out the concentrations of all the species. You know the concentration of H2CO3, you know the concentration of H3O plus, and you know the concentration of CO3 2-. Okay? So we'll stop there for today.